One of the other key features that we think about for graphs of polynomial is their end behavior. The end behavior is referring to what is happening to the function at the far left and at the far right of the graph. So we should be able to describe end behavior without having to graph a polynomial function. There's two really important things that we'll look at that give us clues about the end behavior without even having to see what it looks like visually. The first thing that we have here, though, is some notation that's really important to learn. So we read this with the as the value that's in parentheses up here. So as x approaches negative infinity, f of x approaches, and then in that spot it's either going to be positive or negative infinity. So what we're saying is the graph is either going up on one side or down on one side. And if it's the negative infinity, it would be the left side of the graph. Positive, as x approaches positive infinity, f of x is either approaching positive infinity if it's going up or negative infinity as it's going down. So in the past you might have talked about end behavior and used the words up and down, but as we get more into our mathematical studies, we want to technicalize, that's not a word. We want to be a little more technical in our language there. There's only 4 types of end behavior that we have to know. And we can use some of our parent functions to help us with these 4. So if you remember, our parent function f of x is equal to x is that identity function that has the slope of 1, and it goes right here through the center of the graph. And if you look at the ends of the graph, so again, the end behavior is thinking about what are these arrows doing on either side of the graph. Now, the thing that's going to be a little different about end behavior that we're not used to is that we don't read the graph left to right for end behavior. So when we talked about increasing and decreasing, we said, well, we can read the graph left to right. But for end behavior, we read from the middle of the graph out. So this side would be negative infinity, and this side would be going to positive infinity. And we notice that over here on the left side of the graph, that this is going down to negative infinity. And on the right side of the graph, we are going up to positive infinity. And so this behavior can be generalized to other functions that are similar to this one. So if we go up here and think about our function f of x is equal to x, the a value, or the number in front of x, that's our leading coefficient. So we've talked about our leading coefficient, the number in front of our highest degree. In this case is a positive. And then the degree of the polynomial, well, this is x to the first, that is an odd number. So that means that on any polynomial that has a positive leading coefficient with an odd degree, it's going to be down on the left and up on the right when we think about the end behavior. So let's go down here and look at and think about this function f of x is equal to the opposite of x. And again, this would be a parent function, but now rather than having a positive slope, we have that negative slope. And again, we're thinking about what is this graph doing on the far left. So on the far left of this graph, now rather than going down as we were before, we're going up on the left and down on the right. And so let's go back up here and think about, well, our a value now is not a positive number, we have a -1. So we've changed that leading coefficient to a negative number. But we still have an odd degree because this would still be x to the first power. So if we have a polynomial that has a negative leading coefficient with an odd degree, the graph is going to be going up on the left and down on the right. So this is going to be true for every single polynomial. It doesn't matter how high that degree goes. If it's an odd degree with a negative leading coefficient, it's going to be up on the left and down on the right. And so we're using the most basic, the smallest of these two numbers that we can, because they kind of help us think about that end behavior without having to graph, because we're very familiar with this parent function at this point. Our parent function for the other type of end behavior is our quadratic function. And so if you remember from our studies of quadratics, we are at 0, 0 for the vertex. And if it's a positive, we haven't reflected across the x-axis, so our leading coefficient would be a positive number. And in this case, our degree is even. So x to the second power, 2 is an even number. And so we would describe that our end behavior is going to be the same on both sides when we have an even degree polynomial. And if it's a positive number and we haven't been reflected, then it's going to be up on both sides. So this is going to be true for x to the 4th, x to the 6th, x to the 8th. It doesn't matter as long as it's an even degree. Because again, if we think about the opposite of x squared, when we transform that, that means we've reflected it. And now the graph is going to be flipped over, and the ends of the graph are going to be going down on both sides. And again, this is because we have a negative leading coefficient. So that's the transformation and the reflection. And then we still have an even degree. Those are the only 4 types of end behavior that are possible with polynomial functions. You're either going to have different behaviors on either side or the same. And then depending on the reflections, one side could be going down and the other side could be going up if they're different, or if they're same, they're both going up and both going down. So let's summarize all of that here. So these, again, are the 4 things that can happen. So we can have an odd degree polynomial with a positive leading coefficient, which would be something like our parent function x to the 3rd. And so we know that for our parent function x to the 3rd, if I graphed it, it would look like this. So we would say on the right side of that graph, as x is going to infinity, the output is also going up to positive infinity. And on the left side, over here, that is going to approach negative infinity because it's going down. So this is your notation for the end behavior is going up. This is your notation for it's going down. Either approaching positive infinity for up, negative infinity if it's going down. So our example for a negative leading coefficient would mean, again, that we've reflected. So there's my reflected cubic. And so on the right side, as x is approaching positive infinity, now this graph is going down to negative infinity. And on the left side, as it's approaching negative infinity, the outputs are getting larger. So we would say it's approaching infinity. So again, this would be going down on the right, up on the left. Even degree, we looked at quadratics, but we could also look at quartics. So remember we said that a quartic function would have to have 3 local max or min, so that would be an example of a quartic function. And then you notice there that our end behavior is going to be the same. So if it's an odd degree, it has to be different end behaviors. If it's an even degree, it's going to be the same. As x is approaching positive infinity, so the right side of the graph, it's going up to positive infinity, and the same thing is happening on the left as we approach negative infinity. So this would be up and up when we're thinking about what we're seeing graphically. So the last example then would be a quartic that had been reflected, which means we would have a negative number out in the front. Remember, our negative is what gives us that transformation. So if we're going to be going down to negative infinity, those numbers are going to get smaller and smaller and smaller as we continue to go. So again, without graphing, we want to look at two things. We want to look at our leading coefficient, not leaf, leading coefficient, and the degree. So remember that your degree comes from the highest exponent that we see. So in this case, it's a 7, which means it's an odd. So right away, as soon as I see that I have an odd degree, I should tell myself, well, it's got to be different behaviors on either side. That's what we know to be true about all of those polynomials with odd degrees. And if it's a leading coefficient that is negative, then my brain kind of needs to go in the direction of, okay, it's been reflected across the x-axis. So we can go up here to the table. So we look where we have an odd degree with a negative leading coefficient. So this is going to be approaching negative infinity. And you could even, I mean, like if you needed to, like sketch a picture of that cubic. And just remind yourself, okay, even though it's a 7 degree, it's going to have the same end behavior as that cubic because they're both a negative leading coefficient with an odd. And then you could write the words up and down. So just, scratch work if you need that as you're working. So that should be going to negative infinity. And then on the left side, again, because we're working from the middle of the graph out, that end of the graph is going up to positive infinity. And then for number 2, we again need to look at we'll write the degree first this time. It doesn't matter what you think about first because they both will have an impact on the output. So the degree, be careful, it's not 2. The 2 is written first, but the degree is actually the 5 because it's higher than the 2, which means again we're looking at an odd degree polynomial. And the leading coefficient is the number in front of the x to the 5th, so that is a negative 4. So again, it's going to have the exact same behavior as we had in number 1 because those two characteristics are the same. So as x approaches positive infinity, f of x, or the function, is approaching negative infinity, and as x is approaching negative infinity, the function is approaching positive infinity. So work on memorizing those 4 behaviors to help you think about and learn end behavior.